December 7th, 1941. As the smoke cleared from the devastation at Pearl Harbor, American commanders stared at maps of the Pacific and confronted a new and different nightmare, one that threatened every supply line, field hospital, and forward airstrip before the enemy ever drew a bead. America's industrial might was about to be tested not only in wartime production, but in something few armies had ever solved at scale: how to keep thousands, then millions, of men alive, healthy, and ready to fight in climates where nature itself was a relentless enemy. Canvas tents, hastily erected on muddy atolls from Wake to Guadalcanal, provided no answer. Typhoons tore the tents to shreds in their first storms. 15 inches of monsoonal rain could reduce them to sopping rags in a single night, and the relentless heat and humidity bred clouds of mosquitoes and black mold that destroyed boots, uniforms, and morale. The alternative, traditional wooden barracks, was worse. Slow to build, resource-hungry, requiring skilled labor that simply did not exist on remote beaches ringed with coral and watched by Japanese submarines. The equation was chillingly simple. The U.S. Navy could not land enough men fast enough, nor keep them fighting fit, unless someone designed an entirely new form of portable shelter. In Washington, the War Department hunched over crisis tables strewn with weather maps and catastrophic field reports. Soldiers waded through waterlogged supply dumps or woke with pneumonia on cots surrounded by rotting canvas. The Navy's engineers were given an impossible set of criteria: create a building that could be factory-built, shipped flat, assembled with hand tools by exhausted, often inexperienced crews, and still survive the worst Pacific typhoons and relentless Japanese bombing. It had to be cheap, rugged, quick to put up, and as light as possible. We need a structure that weighs less than a Jeep, fits on one rail car, requires absolutely no foundation, is assembled in a day, costs under $1,000, and stands up to the worst the Pacific can throw at us, their orders demanded. American industry had never attempted a shelter at this scale. There was one precedent: the British Army's Nissen hut, invented in 1916 and tested since the deserts of North Africa. These semicircular corrugated iron shells had proven they could take a sandstorm or bombing run and still house 30 men. But the Nissen's steel panels were heavy, requiring special machinery to move, and its desert ventilation scheme turned the interior into an oven in jungle heat. Worst of all, the Nissen needed bespoke foundations, useless on raw coral or mud. Give us something we can bolt right onto the earth: sand, dirt, coral, anything, thundered Pacific field commanders in cable after cable. American engineers studied the Nissen blueprints, recognizing its core genius while cataloging its fatal weaknesses: too heavy, too dependent on foundations, and simply not equipped for tropical hell. Buckminster Fuller, long dismissed as a crank for his radical manufactured house ideas, now found his basic philosophy pressed into urgent service. Build houses as products, not as one-off projects. Manufacture them like Fords for mass, repeatable field deployment. The Navy's new Quonset Point facility, established almost overnight in Rhode Island, became the crucible for this next great experiment in military engineering. Rhode Island's metalworking tradition proved crucial. Here was access to shipyard-grade steel, corrosion-resistant processes, and immediate proximity to the factories that would become the heart of wartime prefab construction. Naval engineer Otto Brandenberger led the new team, combining the insights of agricultural manufacturers who built tornado-resistant arch barns with architects versed in rapid assembly and officers who had actually survived Pacific storms. The farm building races had already proved that self-supporting steel arches could survive tornadoes, without interior frames, without carpenter-intensive joinery, and without a single pound of wood to tempt the termites and rot. Assembling the first prototype took round-the-clock work fueled by Navy coffee, the frantic sense that every hour lost could mean lives lost, bases overrun, and a strategic disaster for the war's entire island-hopping campaign. Each design was a compromise engineered against disaster. Every pound cut from shipping weight was another hour saved in railcar loading or ship stowage. Every bolt simplified was one less tool for a muddy, rain-soaked Marine to misplace on a beachhead under fire. The challenge was both architectural. How do you bend an arch so it resists not only wind and rain but ground-shaking bombs? And logistical. How do you ensure that a structure can be shipped, unskilled, assembled, and survive both Mother Nature and the enemy's deliberate fury? Their first hurdle was the curve itself. If the arch was too shallow, gale force winds would peel the metal roof off like a sardine can's lid. If too sharp, the interior would become claustrophobic and unusable. Panels would be too heavy, and the engineering forces through each seam would render bolts and joints vulnerable to failure. Even the initial dimensions, 16 feet wide, 20 feet per section, with end walls ready for doors and windows, were defined not by architectural aesthetics but by the hard limitation of the railroad cars used to deliver the kit to distant ports. Every aspect, from the size and gauge of the panels to the placement of the ventilation louvers, was calculated against the twin clocks of looming construction deadlines and the ever-mounting American casualty roster in the jungle. By the spring of 1942, the basic mathematical solution was clear. A perfect semicircle, 8 feet radius, bent from corrugated steel just thin enough to be manhandled, just thick enough to defy a typhoon, and always coated with galvanized zinc to slow the steel's inevitable surrender to salt and rain. The early prototype, assembled by 6 sailors armed only with hand tools, stood in the Quonset Point warehouse, a shape both humble and radical. Brandenburger's arch, built up from lightweight ribbed panels, would anchor directly to whatever ground was available: earth, coral, cracked tarmac. For the first time, a military shelter was engineered not just to survive, but to be everywhere, adaptable, and, as history would prove, eternal. April 1942. The air inside the Quonset Point warehouse vibrates not with the hum of assembly lines, but with the restless energy of a team racing against history. Otto Brandenburger, now confirmed as project leader, walks the floor, dividing the exhausted crew into specialist squads. One group dedicated to aerodynamics and structural calculations, another to packaging and shipping logistics, and a final crew puzzling out joints, fasteners, and ventilation systems. The deadline is laughable: 60 days to design, prototype, test, and validate a new building that might shelter every American fighting man from Australia to Alaska. Failure, for these engineers, is not theoretical. The Pacific has already taught brutal lessons in adaptation. The British Nissen hut's problems, foundation bolts that turned to rust, ventilation that failed in jungle damp, internal wooden frames gobbled by tropical termites, provide a checklist. Every flaw in the enemy's experience must be remedied before the Quonset is ever packed for shipping. The solution? Strip out all susceptible materials, use only galvanized, hot-dipped steel, design access for every bolt and panel so field repairs require no disassembly, and make ventilation so aggressive that condensation and mildew have nowhere to thrive. The design emerges from an iterative, almost frantic prototyping cycle. It is not built on paper but assembled on the warehouse floor. Sketches by dawn, metalwork by afternoon, overnight testing, and immediate revision by the next morning. Aircraft production logic, every part numbered, every step documented, meets agricultural engineering, industrial production, and the brutal constraints of war. The dimensions are functional: 16 feet wide, the limit for a standard rail car; panels under 50 pounds, the maximum 2 men can handle in the field; 48 feet long, adequate for barracks, offices, field hospitals, and storage depots without wasting material or stretching the arch beyond self-supporting limits. The geometry consumes weeks of calculation and debate. If the arch curve is wrong, wind may peel the hut from its anchors or collapse the structure under extreme lateral loads. Too steep, interior headroom suffers, and the ends become hard to close off. The eventual solution: an 8-foot radius for true semicircular profile, yielding 7 feet of headroom at the walls, optimizing both habitability and wind deflection. Corrugated steel panels, each shaped at precise intervals, act as I-beams, resisting bends and crushing loads. Rivet spacing, bolt patterns, stress distribution, every part of the curve is studied and refined against the worst-case scenario, the storm and the bomb. Assembly time becomes the next battlefield. Initial attempts with a wooden floor bog down crews for hours, the first thing to rot in the tropics anyway. The answer: eliminate the floor from the basic design, drop the hut directly on sand, coral, or mud, and offer finished interior options only as a field upgrade. The new format: 96 corrugated panels, bolts, plywood end walls, and a crate with hardware and instructions, can be assembled by 6 men in under 8 hours, dropping unit weight by 1,200 pounds. This is not just engineering, it is logistics, the art of making the improbable routine for thousands of unskilled and exhausted sailors, marines, and engineers. The first complete hut, raised amid stacks of warped prototypes and rejected joints, stands like a challenge to nature and enemy alike. But before mass production launches, the hut faces its own gauntlet. Assembled for wind and snow load trials, instrumented with strain gauges and deflection meters, then battered by March nor'easters. At the crown, the steel flexes less than 2 inches, returning to form as the storm subsides. The joints and panels hold, nothing leaks, and every engineer breathes again. In parallel, field trials in Panama, where humidity remains higher than 85% year-round, stress the hut against mildew, corrosion, and relentless downpours. 6 months later, the official report, minimal corrosion, no panel degradation, but serious problems with condensation, fixed by revising the end wall ventilation and opening new louver channels along the ridge. Ready for full deployment, the prototype is shipped for final approval. On June 10, 1942, amid the most frenetic period of industrial mobilization, the Quonset hut is validated for volume production. Now the supply chain takes over, transforming the shelter from a local experiment to a global reality. Orders pour into factories, George A. Fuller Construction, Strand Steel Corporation, Great Lakes Steel, and others, and by August, more than 40 American rolling mills, bending shops, and assembly lines are producing 1,500 complete kits per week. Corrugated steel arrives by rail, is shaped, galvanized in molten zinc baths, then dried for powder coating and rust protection. Every part is inspected, every fastener checked for tolerances, and every crate packed so a squad of strong backs can move it by hand, from train to ship, from dock to beachhead. In production, every lesson from combat and environment is institutionalized. The steel panels nest inside each other, compressing the kit for tight shipping schedules needed to supply hundreds of bases. End walls with pre-cut openings are packed flat and interleaved. Hardware is boxed with bilingual illustrated manuals, vital for troops from a dozen backgrounds or local labor. The Quonset's instant assembly format is proven in the field. On Espiritu Santo, a CB crew erects a complete hut in a record 4 hours and 17 minutes. But the routine is 5 or 6 huts per day, per team, spread over scorched coconut groves or black volcanic sand. The true achievement, a base that can go from bare ground to full barracks, command posts, or workshops in days, surviving enemy raids, storms, tropical deluges, and the constant stress of frontline deployment. The Quonset hut becomes iconic. By December 1943, as production peaks, streamlined assembly lines and logistical networks routinely move entire bases worth of shelters from Philadelphia factories to New Guinea beaches in under 40 days. The Navy's cost analysis confirms victory. 36 men sheltered for $194 in materials and 60 man-hours versus $12,000 and 400 skilled man-hours for a barracks. At peak, 8,000 Quonset huts flow from factories each month, transforming the built environment of the Pacific War and laying the groundwork for a post-war civilian revolution the architects never imagined. By the summer of 1942, Quonset hut kits stretched from shipyard docks on the American coasts to the untamed Pacific front. Sailors, Seabees, and Marines unboxed steel panels on alien beaches, sometimes under artillery bombardment, always under the shadow of storms. In places like Guadalcanal, the first huts went up within hours, braving coconut groves scorched by battle, and standing as the lone shelter for maintenance crews operating battered fighter aircraft. Field assembly became a choreographed ballet of muscle and improvisation. 2 men prepared end walls, 4 muscled steel arches into place, and the team bolted together overlapping panels, each one designed to align by feel as much as measurement. Combat tested the Quonset hut's theoretical strengths with merciless ferocity. When Japanese bombers strafed airstrips and landed near misses, the curved steel structure flexed, rattled, absorbed the shock, and remained standing while tents and wooden barracks nearby were obliterated. One incident with a 500-pound bomb detonating just 40 yards away saw every tent shredded into scraps. Yet the Quonset hut shaken but intact, with every mechanic inside alive, dazed yet unharmed by direct enemy action. The arch profile was no accident. It deflected blast waves outward, channeling destructive force around the shelter, a principle borrowed from the centuries-old tradition of building stone bridges and mogul domes. The compression ring effect meant that even catastrophic damage rarely led to full structural failure, giving field engineers time to repair bent panels and torn seams, instead of abandoning the entire shelter. Environmental trials were as deadly as enemy action. In the dense humidity of the jungle, condensation pooled inside, raining on exhausted troops trying to sleep. Marines improvised cutout vent holes beyond specification, learning fast that airflow often meant survival. Feedback traveled back to Quonset Point and factories, prompting new models with improved ventilation, larger louvers, and galvanized fasteners for even the lowliest hardware. Every field problem became the seed for factory-level adaptation. In volcanic zones, where anchoring was impossible, crews lashed huts to sand-filled oil barrels, exploiting whatever improvised ground tether could hold when Pacific typhoons howled at 110 miles per hour. The adaptability of the Quonset system shined. What started as one-size-fits-all became endlessly modifiable for soil, sand, wind, and combat risk. Arctic operations tested the hut's limits at the opposite extreme. At Adak, in the wind-scoured Aleutians, the first unit suffered panel cracks from cold, brittle steel. Naval engineers responded by specifying new metallurgies and adding rubber gaskets, while crews learned to install blankets of insulation and run ventilation even at sub-zero temperatures to prevent indoor rain. Desert and European deployments revealed similar adaptation cycles. One ammunition depot in Sicily survived a direct 88mm shell hit, the curved arch channeling force away, leaving the interior twisted but standing compared to the pancaked remains of a nearby concrete block structure. Logistics made the Quonset hut a star performer. As base building accelerated, monthly production peaked at 8,000 units, supporting the Pacific's island-hopping strategy, supply lines, commands, and airfields. A single Liberty ship could carry 200 fully kitted huts, representing shelter for 7,200 men. The average kit moved from factory to front line in just 40 days, a feat unthinkable with any conventional construction. With more than 10 million troops deploying each year, the Quonset became as much a symbol of mobility and survival as the Jeep or the Higgins boat. By war's end, the final tally staggered even the most seasoned planners. 170,000 Quonset huts were manufactured, a concrete answer to the strategic and environmental nightmares of the Pacific, the Arctic, Africa, and Europe. They housed, protected, and sustained not only fighting men but entire wartime infrastructures. Bakeries, hospitals, offices, radio rooms, chapels, ammunition dumps, prisoner of war camps, and mess halls. In a war where survival depended on improvisation, speed, and resilience, Quonset huts proved that architecture engineered for catastrophe could turn into the backbone of victory.